Okay, welcome back everyone. In this video we're going to briefly talk about Kepler's laws of planetary motion and just kind of go through some of the definitions. And I'm going to be using an applet that you can find at the University of Nebraska website, so if you want to you can look that up a bit later. Okay, so Kepler's laws. Kepler's first law simply says that the orbits of planets are ellipses. We used to think that they were circular orbits, but Kepler showed very convincingly that this was not the case. All the orbits of planets are ellipses, with the Sun at one of the foci. So an interesting question to ask is, what's at the other foci? The other focus, rather. So that's something that you can think about and then maybe talk about in class. So if we look at the applet, here we are. Okay, here's Mercury. And what we can see is that obviously this is an ellipse, but if I switch to Venus on the other hand, it's not quite as elliptical. And the number that tells us how elliptical an orbit is the so-called eccentricity, which you might remember from geometry. It's kind of a ratio between the distance between the two foci and the major axis. So we can see, for example, that Earth has almost no eccentricity for its orbit, 0.017, but Pluto has quite a lot of eccentricity. Okay, now you might be wondering, wait a second, Earth was just orbiting, what about Pluto? Well, we have to speed up the animation rate to make that happen. So now it's showing 2 years for every second, and so Pluto actually takes something like, I don't know, 230 years to orbit, something crazy. So that's the first law. The second law is that the planets sweep out equal areas of their orbit in equal amounts of time. Now, next year, you may see a proof of this, but this has to do with a concept we would call angular momentum, which we're not really getting into too much this year. And if we look at what this looks like, then we switch to Kepler's second law, and instead of Pluto, let's set this to something reasonable. I think it was set at 0.2 before. And let's look at Mercury, because Mercury we can actually see what's going on here. Okay, maybe that's too much. Let's slow it down a little bit. There we go. And now if I start sweeping, what it's going to do is start making sectors. And that particular one was 1/16 of an orbit. Okay, now if I click on this thing to sweep continuously, and then if I start sweeping, sorry, there's a little bit of overlap there, but if I erase the sweeps you'll see it again. Okay, now I'm going to pause this here. Take a look at these sectors of an orbit. So what we have is that when we're close to, so this one that I've highlighted, when we're close to the Sun, also called perihelion, because it's perilous to be close to the Sun. During perihelion, well, we're going to be going faster, and we'll talk about that in just a moment, but we're going to be going faster and the radius is less, and those two effects cancel out to give us the same amount of area as, for example, over here. Okay? And it actually turns out that for Earth, we're traveling fastest, we're nearest the Sun right around this time of year, the end of January. And it's very curious because a lot of people think, well, if you're closer to the Sun, isn't that summer? But no. In the summer, we're actually furthest from the Sun. And so if you think about it, what is the shortest month of the year? That's right, it's February. So February is the shortest month because we spend the least amount of time near the Sun at that point. Of course, I'm showing you this on Mercury's orbit because for the Earth, it's not quite as exaggerated. I can kind of zoom out to the Earth, and you can see that these sectors are almost exactly the same size. Okay, so that is Kepler's second law. And kind of a corollary of Kepler's second law is that when the radius of the orbit goes up, the speed goes down, and vice versa. And again, that has to do with conservation of angular momentum. Okay. And finally, Kepler's third law basically says that r cubed over t squared is a constant. And I'll kind of derive this in the next video. And this constant is equal to g times the mass of whatever you're orbiting over 4 pi squared, and this is called Kepler's constant. Now here's the weird thing. Each system has its own Kepler constant. So, for example, anything going around the Sun would use the mass of the Sun and have one constant. Anything going around the Earth would have a different mass because of the mass of the Earth, and that would be a different constant. If you tried to get something to orbit around your head, well, good luck, but you'd use the mass of your head. And this is actually how we determined the mass of Jupiter, because anything that goes around Jupiter will conform to a Kepler's constant using the mass of Jupiter. Okay, now one thing that's kind of cool about this is if we measure the time in years, and if we measure the distance, the radius of the orbit, in a weird unit called an astronomical unit, also known as an AU. And just as a side note, 1 AU is kind of the average Earth-Sun distance, and that's 1.5 times 10 to the 11th meters if you're curious. But if we measure time in years and radius in AU, well, here's something awesome about the Kepler constant for the Sun. It turns into 1. Okay, but this is a very, very dire warning. Make sure that you're using years and astronomical units for your units. Okay? If you're not doing that, if you're using meters and seconds, then you do have to use the full Kepler constant. If you don't, you're going to be sad. Okay, so that kind of wraps things up for Kepler's laws, and in the next video I'll show you where this r cubed over t squared actually comes from.